So can we start? It's 48 and waited for almost 5 minutes. So I think we can start the class. What do you say? Should I start the class, guys?
Yes, sir.
Yes, sir.
Yeah, so let me present first. So in the last week, we started with pressure measurement. And initially, we talked about the basic principles by which we generally measure pressure. Okay, so one of them is converting that into balancing the liquid column. We also do that. And so on. We have, as I've already talked about, two things. One is the balance of liquids. We try to understand how it works and all, right? But later, I also talked about the calibration instrument called the weight test. So today, I just wanted to very quickly present you the calibration and how people will do it, so that you'll get a good idea of what it is basically. Okay, so I'm trying to play this. So you can see here, this is the what we call as a dead weight tester. This whole element is what we call as dead weight tester.
Sir, your voice is very low.
My voice is pretty low. Huh? 1 second.
Yes, sir.
Just a minute. Is it audible now?
Yes, sir.
Is it clear, or last week it was better?
No, sir. This one is clear.
It's fine now, sir, I guess.
I think it's fine. Okay. So now I will try to recall what has been taught in the last class. We understood the basic principles. Can somebody record it? Possibly. In the last class, we have discussed about pressure measurement. What is the basic principles on which many of the instruments are actually working, like fluid column balance, like elastic elements, elasticity properties relating with pressure, so on and so forth. We have already studied those things, but they are the very fundamentals on which most of the measurement instruments are being built up. Okay, and we have also discussed about the fundamentals of fundamental principles of the liquid column balancing, why it helps us to actually balance, and we will continue studying those things. And apart from that, we also studied about the dead weight tester, which is a calibrating instrument. And you have many questions like, sir, why it is very precise? Means the instrument is made such that the very purpose of this dead weight tester is itself to calibrate the pressure measuring instrument. Okay. So if anyone asks you to calibrate a pressure measuring instrument, you have to take it to a dead weight tester. That is a fundamental. So I just wanted to show you how it works in real time in the lab kind of a thing. Very quickly, I will go through it. So this is basically your dead weight tester, and now whatever they are keeping it here is basically an arrangement to put weights. Okay, so base and weights they want to put it. So they kept it in a particular shell to make sure that it is dust free and all. So if it accumulates dust and all, it will be more. So this is basically the adjustment piston, and whatever we have seen now, the piston arrangement is this, where on top of it we are keeping weights, and this is the piston which applies pressure inside the liquid, and these are all the vent holes. Okay, these are all the different holes to take out the air that is present within the system when we are not working. So to drain off the air that is inside present inside, we will keep that. Now whichever gauge we want to test, that we are actually keeping mounting onto the dead weight tester. You can see over here is actually mounting the dead weight tester onto the top. Okay, so now what they will do is, now the principle we know, we keep the weights, known weights, precisely measured weights onto this piston, and because of that the pressure will be varied, and therefore by applying suitable amount of pressure onto this, such that this weights will float on the system, which shows equivalent reading in the instrument itself. So now he has taken 10 bar pressure. Okay, for example, he has taken 10 bar pressure. Now what he is doing is they are kind of unwinding everything, all the walls, they are kind of opening it. Okay, you can see there, they are kind of opening all the walls. So exhaust, they are doing priming such that the exhaust air, whichever is present inside, will be eliminated. And if the oil cup, which is for filling the thing, if they are having any air inside, they are kind of locating, then we are there just closing the walls, all the walls. Okay, so now they are they're kind of doing some ramming such that the exhaust pressure, whichever is there, that will go away. So now you can see here, once the air is gone, this needle makes a small move. You can observe here again. So there is a small movement of this needle. So that means the air is almost taken out. So now rotate the X bar. This is what we call it, the X bar, which is what we call it as clockwise. So we are applying some pressure onto that, so that this liquid will pump into this bar as well as into this. Now after rotating to close to 10 bar, we are kind of rotating this shaft such that the frictional effects will be negated. So to take out the frictional effects, we are actually rotating this, and then when you are rotating, you can see the X bar reading over here. What is the X bar? So now when it is rotated further, you can see these weights will be taken up slightly up. Okay, you can just carefully look at this. Now we started. So let us see. Yeah. Now let's just observe again. So it kind of floated once it moved, right? So 10 up to 10 bar it is going. So we are applying pressure close to 10 bar. Okay. When we are closing it to 10 bar, we are making it to rotate. We are not up to 10 bar because we know that this is the pressure that is equal to that move. Now you can see that just the movement of this has actually created the floating of this lever. So therefore we will just so now X bar is we have to adjust the pressure to 0.0 megapascals. So that is basically your 10 millibars millipascal pressure, whatever is there, that is being given. This value and versus this value, we will note it down. So for exactly this one, how much it is showing, that is what we will show here. Now they are kind of increasing the weights to 20 millipascals. Yeah. So now what they will do is load a 20 millipascal weight, and again they are rotating such that whenever it comes close to 20 bar, okay, now they are kind of start to rotate it. So when they are rotating, slight movement, now you can see there is a floating of that, you can see. Just it starts to float. Now you can see there the needle is not exactly 20, 19.9 or something is there. Okay, so when that is there, you can note it down. 0.0 mm it is showing. So the figure is fixed. So record the data, whatever you are finding, 19.95 or something, whatever it is showing, 20 millipascal. Likewise, you keep on loading this. Okay, finally the highest pressure, and this is your calibration curve. Okay, and then when you are taking out each one, you will also find out the hysteresis effect. Now while you are taking out this weight, initially it will not be the same, it will keep on changing. So there is a hysteresis effect. So whatever, when you are going on increasing the load, when you are decreasing the load, the curve will not follow the same thing, and the difference between each thing is what we call it as the hysteresis effect. Okay, so this is all about slightly about the dead weight tester working. You can see so many videos are there, you can just go through them. Now let us move on to the so this is what we have talked about. Now the dead weight tester, where we are rotating this X bar, and this is the pressure and this is the weights, and how it happens is different winds are there. So by applying suitable pressure, this by putting some weights, it will pressurize. So by rotating it along the x-axis, so we are creating the pressure such that it balances the weights of this. When it balances, there should not be any negative the frictional forces. So we are rotating the shaft such that whenever it's floating, the value will be shown over here. This value versus this value is what we are actually drawing on a curve. What is the input and what is the output. That is what we are drawing on a curve. And based on that, we'll find out what's the deviation that we are getting for each reading. And from that, we try to find out a curve. From that, we'll find out using regression analysis, we will give an equation and say that how much R square that regression value will be having. From that, you will be able to use that for unknown pressures, used to measure unknown. That's what we do. We also looked at manometer, the basic principle, fundamental principle. With the manometer, we have looked at. Now we will quickly go to finish the manometer this thing. So you can see, yeah.
Yeah, something is there in chart.
Check. Okay, sorry, we should have. Now let me start. Anyways, that thing you can directly see in the dead weight test working. You can see in the easily you can view in the YouTube. There are so many things. It's not a problem. You can listen to that and you can understand. Just I want to show you how the lab will do it. And the five fundamental principles on which manometer works, we have already studied. So pressure is a very common measurement system where we have to manually look at the height variation or the imbalance that happens due to the pressure difference within the manometric levels in a uniform cross-sectional tube or in a varied cross-sectional tube. So by which we will be able to find out the pressure difference across the tube. Okay. So now you know that any liquid can be used. So we have already discussed we are trying to use a manometric liquid which is having more density such that we don't need any lengthy pipe here to be used. Okay, so manometers are devices in which columns of suitable liquid are used to measure the pressure difference in pressure between 2 points or between a certain point and the atmosphere. So we may be able to use this for finding out the pressure difference between the atmospheric pressure here, atmospheric pressure. My arrow is being shown, right? So atmospheric pressure, okay, and pressure within the tube. So I assume that this is a tube and the liquid is flowing like this. Okay, we have just written the cross section. So here we have put it here and therefore it actually, so did anyone got a question? So should we put like this or this horizontal is also fine? What I'm asking is, if there is a tube, should we connect this tube to like this, or if there is a tube, it has to be connected like this? Which one is the correct thing? Or any variation if we vary that? Think about it, ponder over it. Okay, so now I will continue. So what exactly we are utilizing over here is, what we are doing here is, this is the pressure for which we are actually finding at a particular point. This is an example for finding pressure at a particular point in the inside a tube. Is it the average pressure or the local pressure? Are we finding out the average pressure or the local pressure? Horizontal level will have a pressure over here. This is having some more pressure. So what is exactly we are finding? Okay, let's think. So now in this manometer, what we are doing is, the fluid which is passing through a tube and one of the side is connected to a U-tube manometer, and this is actually filled with basically a manometric liquid which is here, and it is immiscible. It will not mix with the liquid that we are using it. So its vapor pressure is also and then now what is happening is, when the pressure on this side is higher, automatically it applies more pressure. Therefore, this liquid will accelerate. It tries to fill this tube. It will try to push this tube, and then The other side, since it is an incompressible fluid, the amount of liquid that is pushed down will be rising on the other side. Okay? So now we are taking that as a base, one level as base. Either this side we are taking as a base, and from there we are trying to find out what is the difference between these two liquids. Okay, and then we will find out what is the exact equation for finding the pressure difference. Now you can see over here, this is taken as a level over here. Now this part is taken as a level over here. We are considering it as a base. Okay, from this I am trying to find out what is this level and what is the height over this level. Okay, center part, central line. What is the pressure? So from this height, I am taking this total height. Let us say this is H1, and this is, let us say this is H2. So the total distance between these two levels is H1 minus H2. The same thing we have written, like from here to here it is X, and from here to here it is Y. The total is X plus Y. So that is what we are taking. Okay. Now from this, what is the pressure up to the central part of this? If you want to measure, it is nothing but at a static level on this level. What is the pressure that is acting? The pressure that is acting over here is nothing but your density of the fluid, because taking the hydrostatic law, it is nothing but rho GH. So we have the P1, the pressure that is acting, and this liquid that is acting from here. This is P1. Let us say this is what P1. We don't know what is P1. So this is P1, and P1 plus the column, whatever is there, the effect of this column's pressure on this manometric liquid on this side I am trying to find. So that is nothing but rho into A, that is the density of the liquid that is here, into its gravity, and the height, a column of this. Up to here it is P1, that is acting as P1, plus rho into the column of the liquid and take the density into the column height into the gravity. So this will give you the pressure. So P1 plus the pressure P1 plus this one will be equivalent to, now I am trying to find out on this side what is the difference. So this height is equivalent to, up to here the pressure that is acting is P atmosphere. If it is not atmosphere, we have to write down whatever the liquid that we are having. Suppose if the similar tube is here on this side also. For example, what I want to say is, if there is a tube like this, let us say this is P2, P2, this is P. Now what I have to take? I have to take what is this pressure is P2 plus whatever the liquid, that pressure I have to take. Instead of this expression will become like P2 plus whatever the liquid in the B, that is rho B G, into whatever height it is basically. So whatever the distance it is will not be exactly expressed by some distance. Okay, plus after this whatever height we have is rho B, that is the manometric liquid. So since rho A and rho B are same, I can take rho A G, and what is the height into X. Rho A G into X. So these two will give you what? Now the first case, it will be nothing but, first case, this case I'm talking about, P1 minus P atmosphere is equal to rho B Gx minus rho A G X plus Y. It is nothing but, since the rho A and rho B are different, okay, here they both are different. Rho B is different. Here rho A is basically your liquid in the fluid. So this is basically this rho B only. So this rho A is nothing but this liquid, this column. This rho B is this rho, this rho. Okay? Instead of this. So therefore, if you can write this expression in this form, you can find out the difference between the pressure difference between the fluid and the atmosphere. Because it is open to atmosphere. The first case is open to atmosphere. When it comes to the second case, you can write it down like P1 minus P2. The thing that I have done. P1 minus P2. Is equivalent to P1 minus P2 equivalent to what? Rho B Gx plus rho B, not rho B, you can take it as C. Okay, this will also become C. Don't get it. This will be, let us say this as C. Okay, so rho C G x plus y. For this condition, if you are taking the both are same, suppose in case rho C G x plus y plus P1, this P2 has gone this side, so this one minus rho A G x plus. I'm really sorry, mouse able to write down the expressions better. Okay, so now what is that we are getting is the pressure difference between two pipelines, P1 minus P2. So this is how we will write the expressions, and then we will find out the pressure difference between two pipelines, or pressure difference between what we call the pressure difference between pipe and the atmospheric pressure. Okay, the same thing I have written here. So the problem is to make very accurate measurements. The things that will actually get into picture is the temperature. Okay, what is the temperature? That is more important. And then we also have gravity effects and capillary corrections are to be made. So since capillary, that means these capillary effects are negligible for pipe diameters greater than 20 mm. So when you have taking pipes which are greater than 20 mm, we can neglect the concave or convex surface that we get because of the contact angle of the fluid. So that will be vanished. So therefore, we can actually take into a horizontal, exactly horizontal liquid. Otherwise, if it has some capillary effects, it will be either in this shape, like capillary effects like this, you can see. So you don't know which level you have to take, exactly this level or this level. So because of this, some error may come into picture because of the levels. This happens due to the contact angle, of the liquid. So now, what we are trying to do is, if you take the size of this diameter of these pipes more than 20 mm, for example, so we have these effects taken care of. Okay, the capillary corrections are taken care of. No capillary actions will be seen. Gravity is basically dependent on the orientation. So if you are orienting them properly, there is no issue with that. And temperature, basically why the temperature effects will come is, if you put a temperature, because of the temperature also, the liquid tend to expand. Okay, so how do you know that correction? So that is more important. So those temperature effects also should be known. Okay. So if you know all these things, then you will get very accurate results. Generally, the temperatures are not too high. So if you are to eliminate the temperature effects, we will be working these C2 parameters in a relatively room temperature conditions and all. Not go to very high temperatures. We will not use this kind of instruments. Okay, gravity, we will make sure that they are in the correct posture or position, so that the gravity effects will be negative. So these are the things that you have to take care of. Suppose I am giving you a very simple example over here. We have an air tube manometers which is having specific gravity. What do you mean by specific gravity? Density of the fluid by the density of the standard fluid, which in general we will take it as water. So this will be 820. Okay. So what is he saying is, one limb of the manometer is exposed to an atmospheric pressure of 740 mm of Hg. So one is atmospheric pressure. Okay, one is atmospheric. And the second one is the difference in column heights is measured to be 20 centimeters plus or minus 1 mm when exposed to an air source at 25 degrees. So what he is given is, he has said that the column heights they have measured to be 20 centimeters plus or minus 1 mm. So you know that the difference is 20 centimeters, and then you also have a variation of plus or 1 mm. So the deviation also he has given. So what is the difference in that is also given. Okay, so when exposed to an air source at 25 degrees, calculate the pressure differential in PA and what can be its uncertainty. So that is what he is asking. Okay, so think of it. How can we solve this problem? So you have 740 this side. You are given the specific gravity. Okay, specific gravity as a manometric fluid. So you know what is rho m, manometric liquid rho m, you know. So other thing is the difference in column heights is measured to be 20 centimeters. So you know it is a difference in the height. So they are just asking you to find out what is the pressure differential. So the difference is only 20 centimeters. So you have to write the expression, take a balance of that, and then from then you can find out the, first you find out the pressure difference, and using this 1 mm deviation, how much effect it can have. This is for 20 centimeters, it is showing 1 mm, and so the pressure, how it will be affected. So that you have to calculate. Okay, take time and we will do this, we will solve this problem. So the second question in the same thing is, if the above manometer was carelessly mounted with an angle of 30 degrees to the vertical. Suppose if I am varying this by 30 degrees variation, so it is not vertical, instead it is slightly inclined by 3 degrees to the vertical. The vertical axis, if you are making 3 degrees error. So what is the error in the indicated pressure due to this corresponding to the data given? So for the same data, if the tube is not vertical, but it is 3 degrees inclination with the vertical, what can be the error that comes to the picture? What is the gravity error that will be in the picture? So that is what is asked. So I have given the solutions here. Go through the problem. Just think of this problem. We'll solve it. Okay, next one is we will continue. We'll complete this and then go to the problem. Now, the different kinds of variants in well-type manometer, and then we have inclined manometer. So as I told you, in this one also we have already discussed in the previous class. So what happens if the tube is not of uniform, what we call it, if it's not of uniform area, uniform cross section. So as I told you, if there is too much of pressures on this side, if you have too much of pressures working, so then what happens is, you may have to have a long pipe. Instead of long pipe, what people have discussed and tried is, what if we have a bigger reservoir kind of a thing here and then a small tube? So that's what the change they have. Initially, the liquid is making a difference of H because it is having more cross section. They both will not be of the same level unless in a uniform tube. In the other YouTube manometer that you have seen, the tube diameter is exactly equivalent to this diameter up to this line. Therefore, the height of the liquid because of these pressures are on the same length. But now what is happening? There is a difference in the pressures, okay, because the area is getting changed over here. So therefore, now what happens is basically when you are applying pressure, okay, when you are applying pressure from this side, it is reduced, it's lowered by this small amount, and therefore there is an increase in the height by this amount. Okay, sorry, I just made a mistake. So when both sides are the same pressure, they will be at the same level, no matter what the whatever be the cross sections. Okay, so here and here it will be the same. I got in hydrostatic law. Okay, now when the pressure is applied, it is reduced by a small height h dash. Okay, since the area of the fluid within this, the volume of the fluid here is nothing but its area into H dash. Its area into H dash. What happens? Here the volume of this tube is lower, therefore more amount of fluid will, the height of the fluid that raises will be more predominant in this pipe. Okay, the height is not as small as H dash, but it is higher because the cross-sectional area is reduced. Okay, so the same amount of fluid, it is incompressible, so that same amount has to go. Here the area is higher, A into H dash is equivalent to the area of the tube into H. Since area of the tube is lower, to balance that, H has to be higher. Okay, so this is area of the reservoir, AR, let us say, into H dash is equal to AT, area of the tube into H. So since the tube area is lower, your H will be higher. So now if you keep those two things into the expression, okay, the same thing. I'm really sorry. Okay. Now you write down this. You know what is the volume amount of volume that is displaced from this. From this you can understand that it is H into A dash or H dash into capital A. I'm taking. That is basically this total volume of the fluid that is displaced is equal to H into A. So now the pressure P is acting over here, okay, plus rho A into GH. So up to the air column, whatever is kept over here. So the density of air into G into gravity up to H. So this area, this is almost equivalent to the same thing. So up to here, whatever rho A into GH, and then up to here, okay, and then it is nothing but rho A, which is nothing but the density of air into G into H dash. Okay, G into H dash. Rho A, the density of air column, into G up to H, it's the same, and the extra thing I am writing, so it is nothing but rho A into G into H plus H dash I can write directly, which is equivalent to, on this side, the pressure that is acting is PA, the atmospheric pressure that is acting over here, plus the manometric liquid, whatever is having is rho F G. I'm taking this as a balance, so the total thing will be H plus H dash. This H plus, since I'm taking this as my base of the base level, I'm taking this. So the total column of fluid above this is rho A, that is the pressure acting here, atmospheric pressure acting here. Okay, and into G into, so you may get a doubt, sir, why we are taking rho A here? Because here we are assuming that it is some air, and here we are assuming that it should be some, it's basically atmosphere, open to the atmosphere. And since we know the atmospheric pressure, we are directly taking the atmospheric pressure into picture. No need of column and all. So because of this, how much pressure it will be acting on this, we know. So therefore, directly PA up to here we have taken. And then the manometric liquid into height from the base level. So that is H into H plus H dash into G into rho F. So therefore, the pressure P is P minus PA, or P, the pressure difference P minus PA is equivalent to nothing but the manometric difference rho F minus rho A. Okay, manometric difference into G into H plus H dash. So this can be written as 1 plus H dash by H, which from this expression is nothing but small a by capital A, plus a by capital A. So now from this expression, what we can say, if a by a is very small, for example, let us say this small a by this area by this area is very small. So compared to this area, this is a very large reservoir area. Then what happens? 1 plus very small thing, there will be some error, but we can always negate this. Correct? So therefore, we can directly get pressure equal or P minus PA, the differential pressure between the fluid and the atmospheric pressure is equivalent to the difference in the manometric liquid to the air, to the density of air into Z into whatever height H that we have, that we can get. So if we know what is the height it has raised from the earlier thing, so from that we can directly find out what is the, so whatever height that we have, which is reading only from one level. If you know this, you can directly measure. Don't need to find out. Clear? So we know the initial reading, we will mark that, and then when applied the pressure, how much it has raised. So immediately the density of this fluid minus the density of A, whatever the pipe that is connected for the fluid, into G into what height we have. So this will have slightest error because we are not considering small a by capital A, but that is okay. This makes things very simple. So this is called as well-type manometer. But the other thing we also have, so what can be done when the manometer is inclined? What will, suppose if it is inclined, what can be done? Now, we know that the pipe is inclined over here, this part. Now H is equivalent to, initially they both are at the same level. See, the liquid level is like this, it's horizontal. So initially they both are at the same level. So when some pressure is applied, there is a volume of fluid that gets dipped, okay, by H dash, and the same amount of volume will raise in this. Since the pipe is making an angle of theta, here there is a R column of liquid has risen. Okay, so this R is what the length of the liquid that has risen, the inclined. So now if I want to convert that into a vertical height, it will be given by H is equivalent to this height. This vertical height is given by H equivalent to R sin theta. Okay, since we know what is R, we know what is R, and we know what is theta from the angle of inclination with the horizontal. We can directly put into this expression H is equivalent to R sin theta into the equation, and we can directly know what can be the pressure. So these are the different kinds of YouTube manometers that we use in the directly we will use in the pressure measure. Okay. So now this is what we wanted to want to solve in the previous thing. So let us look at this. The solution of this problem. So the second part I am trying to solve over here. The first part is straightforward, you can solve this. The second part, what we have given is B, if the above manometer was carelessly mounted. Okay, if the above manometer was carelessly mounted with an angle of theta 3 degrees to the vertical. Okay, as I told you, it's vertical by 3 degrees. What is the error in the indicated pressure due to this corresponding gain? So what he is saying is it is making an angle of 3 degrees to the vertical. So which will be it is making an angle of 3 degrees with the vertical. Therefore, it becomes H cos theta. H is equivalent to R cos theta, whatever the rise in the equation by into its angle. So the column height is measured to be 20 centimeters, for example, and it is 3 degrees inclined to the vertical. Therefore, if you want to find out the vertical, it is nothing but H cos theta over here. So H is, I converted that into meters. So therefore, cos 3 degrees centigrade, it is nothing but 0.1997 meters. So that is what your H. So now find out the pressure difference between these two. P minus PA is equivalent to rho m manometric fluid. What is the manometric fluid? This thing is already given as 0.82 as a manometric fluid. Okay, manometric fluid. He has mentioned the specific gravity to be 0.82, and therefore it should be 820. Manometric liquid is 990. If generally we take it as 1000 density for water, but to be accurate, it is around 990 or something, 999 or something. So therefore, if you multiply that with this 999 or something, 0.99 or something, so you will 999 of 0.82, that will give you around 816.7. Okay, that is, suppose if you want to take 1000, you take it, no problem. You can take 820. Okay, and from that, what is the other thing that you are measuring? Air source. You also mentioned that it is air source. Therefore, what is the density of air? 1.15 kg per meter cube. Into G is 9.81. Into H cos the 1596.3 pascals. Okay, 1596.3 pascals. So can you calculate the same expression with 0.2 here? Can anyone tell me what is the value of this? Quickly. Eight 116.7 minus 1.15 into 9.81 to 0. Is close to 1600.91 by 1600. So we have already got this to be 1596.3 Pascal, and we also have the same thing we have to do for finding out the pressure difference in pascals first. So for finding out the pascals, what we have done, the height reading is given between 20 centimeters plus or minus 1 mm. Okay, so this is 20.1 is the maximum and 19.9. In between that, this reading will deviate actually. So if you substitute that, we have already got 1598.5 is the reading that we have got from the correct positioning of the vertical, and by 3 degrees variation we got 1596.3, therefore minus 2.2 pascals because of this mounting. So this is the error that we have got because of the. So when this 2.2 divided by 1598.5 pascals, so it is creating around 25% of the error. So it's not 25%, no, 2.2 and what is 1598.5. So that is not too much of it, 2.5%. Right? Anyways, you check that. Okay. Anyways, you check that in the question. So this is basically your problem, whatever I have to do. The answer I have given over here, you just have a look at this. is equivalent to Z2 into Z2 by sine theta into E2. This makes sense, right? If you take X if you take here, this will be nothing but your area A2 into this X has to be written, right? This is the height, X sine theta is to be your height. Okay, X sine theta is your height, and whatever the area that is there, that if you keep it, then it will be equivalent to this volume is equivalent to this volume. So that I am writing in terms of Z2. Therefore, it becomes Z2 by sine theta A2, which is nothing but X into A2. So this is the height. Okay. So Z1 into pi capital D square by 4 is equivalent to Z2 by sine theta into pi small d square by 4, which is nothing but x small x into pi d square by 4. From this Z1 pi capital D square by 4, pi by 4 will get cancelled, and whatever is left over is the Z1 is equivalent to Z2 by sine theta small d square by capital D square, which is nothing but x into, x is the rise of the liquid in the fluid, into d small d square by capital D square. Therefore, P1 minus P2, we have Z1 plus Z2. So Z1, I am substituting x into Z2 is basically is nothing but x into sine theta. So x into sine theta. Z1 is nothing but this variation is nothing but x into small d square by capital D square. So therefore, you can write it down that rho manometric z into x, I am taking it as common, sine theta plus d small d square by capital D square, which is equivalent to density of water into z into, this is the pressure that we have. So the same expression. Okay, this one I'm writing in the form of this. So therefore, what you are getting H is basically this value. So the head being measured is 3% of 3 mm, which is equivalent to why 3% of 3 mm. This is mentioned that it is around 3 mm of water. So whatever the head that we are getting is 3 mm of water. Therefore, we are trying to find out the head of that in terms of that is basically nothing but your height in terms of your you are converting that in the deviation, you are converting into possible meters. Okay, so that we are doing, and then if you substitute these expressions into that, you will get theta as 7.6 degrees directly. Okay, so why 3% only taken? The 3% represents the smallest measurement possible on the manometer. So it is inflicted. So we were in our problem it is given as 0.5 mm. So that means we are taking it as 0.0005 meters. Okay, so therefore 3% of 3 mm why we have taken. So that is the minimum measurement that we can take on this side H, and this side whatever we are measuring is 0.74 into 0.0005 is given over here, and the d square by capital D square is given over here. So sine theta we need to find out, which is equal to 7.6. So we need to give the inclination to be 7.6 degrees to make sure that we are having the desired accuracy, which is desired accuracy is 3%. Clear? So we will see in the next class what are the things that we have to take care while measuring your Nietzsche manometer. So what are the accuracy factors that we should look at? Those things we will see, and then we also look at the dynamic response. Okay, these principles we know. How the dynamic response of the pressure measurement system will vary. So these things also we will have a look at. Okay. So any doubts in the problems we will discuss, and tomorrow's first hour we will discuss. And then we will try to find out vacuum pressure measurement, which will complete this complete lab, which we will try to cover this weekend. Okay. So please go through the. I will send this. I've already sent it, right? I've already sent it out. So please go through the this whole thing, and try to solve these problems. So if you have doubts, we will discuss into those class. Okay. So that is it for today. We'll meet tomorrow at 9 to 10. Okay, I have another meeting at 2:30, so I have to go. So any doubts that you have today, we will discuss in tomorrow's morning. All right. Right. Then take a leave from you. So tomorrow's class, 9 o'clock, 10 o'clock, we will meet and discuss the doubts that you have in this today's class. Meanwhile, I will upload also. Just go through that, and whatever doubts you have, you are free to discuss. Right? Take care, all of you.